Все, поехали.
А я не вижу, что запись идет.
Рассказывай. Красная точка горит в верхнем углу. Так, ну сегодня у нас Сергей Петрович Царев рассказывает, ему передаю я все права.
Thanks, Oleg. Thank you very much for this possibility to give one more presentation of quite new but very simple technology. I did expose it several times in Russian, but this should be an English language exposition. It will be somehow an informal continuation of my previous talk about polynomial filters and boundary effects of polynomial filters. So the topics to be discussed are the following. Certainly we'll solve the main problem of this talk, how to find a precise position of some navigation satellite at some particular time, provided we are given just 2 points of its trajectory. And we want to restore the complete trajectory between 2 points with high precision. So the standard problem of interpolation. The obvious and very practical in a sense solution is just try to solve the respective dynamical system. So model all necessary forces acting on the satellite, all additional effects, etc., and solve the two-point boundary value problem. But in fact, in this particular situation, it's quite difficult due to the fact that the models of forces are quite complicated. And also, as rotation is not that trivial when you come to the necessary precision. Sorry, guys, can you hear me? Hello? Anyone present?
Yes.
Sorry, okay, because I see only my screen. Good. So this is a practical but quite complicated solution. And we propose a new, very simple and very easy and very fast method based on linear and nonlinear machine learning approach. Using this method, we overcome this problem of boundary attenuation exposed in my previous talk. In my previous talk, I tried to find defects, outliers, jumps in published trajectories of navigation satellites. And unfortunately, we see that all linear filters which we were able to construct have some boundary effect, which prevents us to see such outliers and such defects near boundaries. Then we briefly, if time permits, extend our interpolation methodology from dynamical systems, so one parametric trajectories, to multi-parametric continuum medium and other phenomena. We'll try to model ionospheric delays for navigation signals. Then a few words about possible methodological interpretation of our approach and some problems of big data in machine learning will be briefly mentioned. So all such topics will be given in the following way. First, we'll give the simplest possible example of new methodology, which we call free interpolation. Namely, we interpolate the trajectories of GLONASS and GPS satellites with high precision. So what is the difficulty of calculating the orbit with the necessary accuracy? What are input data to be used in such calculations? Can we get precise trajectories from somewhere? In fact, standard recommendations and quite good recommendation I use the standard classical polynomial Lagrange interpolation. We will discuss differences, positive and negative effects, and compare accuracy of classical Lagrangian polynomial interpolation and our new free interpolation technology. Then we will move much further to nonlinear free interpolation, and we will solve the problem of two-point boundary problem for this dynamical system, namely, given 2 points of the trajectory, restore all positions of the satellites in between, using very simple solving ODE approach. So, using this machine learning approach, we will show how to overcome this boundary attenuation effect of polynomial filters. Then we will come into more philosophical, I would say, very quite deep problem of machine learning. If we speak about free interpolation, but still we impose some form of interpolation, namely polynomial form. Why we are so restricted, and why we cannot make absolutely free interpolation model? Then the second main problem of big data come into play. Certainly we all understand the first main problem of big data, namely there are many of them, right? Megabytes, terabytes, and petabytes. But the second main problem of big data is the fact, which we will see quite easily, that they are in fact very scarce. There are too few of data in such terabytes, because in multidimensional case, and we are in multidimensional case, as we will see, number of data which one would need mathematically in a simple mathematical model of free, absolutely free interpolation would be enormous, not petabytes and not exabytes, but very, very high volumes of information if we will follow a naive approach. Also, some methodological aspect will be exposed. Namely, it's possible to say that this free interpolation is nothing but the classical linear and non-linear regression, very well known in data processing, in statistics, etc., etc. Well, we will discuss if this is true. And finally, we will try to generalize our ideas to the multidimensional case of continuous media. Good. As I told, the main object of our study today will be trajectories of navigation satellites of both wide well-known system GLONASS, GPS, and finally, no difference with Beidou, Chinese system, or European Galileo. Formally, I would say, as it would be ideally, if they will ideally exist, the nominal trajectories of GPS satellites will be just circular orbits with quite big radius, 26,000 kilometers and more than 26,000 kilometers from the center of the Earth. So quite large, but not as big as geostationary. Geostationary orbit is 41 and something thousand kilometers from the center of the Earth. And for GLONASS trajectories, it's practically the same. Also circular orbits, bit smaller period because the radius is a bit smaller. And inclination, by the way, of trajectories to the equator is different, a little bit. But reality is much more complicated. Orbits of all satellites are, in fact, cannot be circular. Even if we will approximate them by elliptic Keplerian orbits, then we will have varying eccentricity. Dynamics of spacecraft is affected by very complicated forces. So deviation from ideal circle or even ideal elliptical orbit will be several kilometers in the minimum. There is no possibility to have high precision and even modest precision navigation using these simple circular and elliptic trajectories. Let's have a brief look at the satellite dynamics, namely for navigation satellites on quite high trajectories, more than 20,000 kilometers above the surface of the Earth. So the first line in this table just exposes the main central gravity force of the Earth in the ideal setting when the Earth is just an ideal ball. But in fact, the Earth is not an ideal ball. It's more like ellipsoidal body. So this is called, this difference in gravity force called second zonal harmonics. It's quite big. It's not, well, absolutely big. But it affects, in the last column, we will see the effects of such perturbations. Namely, the perturbation in 1 hour of flight, of 12-hour period. In only 1 hour, this non-sphericity of the Earth results in very big deviation in 300 meters from an ideal orbit. Also, obviously, tidal forces from moon and sun result in quite large variations of the orbit, 40 meters for 1 hour and 20 meters 1 hour respectively. Also, higher order harmonics of the Earth gravity called fourth zonal harmonics and gravity anomalies, result in quite a few centimeters, 60 centimeters deviation from some ideal orbit. The line solar radiation refers to the light pressure. Certainly it's very small in our usual human interpretation. But in space, when there is no other forces and the flight is free and the sun is shining always, we will see that for 1 hour flight, we will have almost 60 centimeters of perturbation, relative naive approach. And all the other anomalies also have quite serious influence. Right, let's go ahead. So reality is complicated, but what about possibility to obtain such information? What is the standard accurate information about real orbits? Yes, it's possible to obtain such information, and it comes regularly in open archives, and they're just usual text files called SP3 files for all GPS, GLONASS, Beidou, and other satellites. Every day with the 15 minutes time steps, coordinates of every satellite is given with quite high precision, namely claimed accuracy, so deviation of some real, what is reality is difficult to say, but it's about around 3 centimeters. And an obvious question is possible to ask, is it an excessive precision, 3 centimeters, when we have so complicated forces? And in fact, is it really needed? I will give just a screenshot of a very old paper published in Geophysical Research Letters in 1999, so 20 years ago. It says that it's possible to use GPS navigation for geodesical surveying, so very precise positioning of your receiver with 1 millimeter precision. Okay, it's a good paper, old paper, but it's very instructive to look into the table on the last page of this paper. So we see the table. The first column is a date of methodology applied, and the second is just precision. They are interested in vertical precision, in displacement somewhere in California. They will try to monitor movement of the Earth, just to monitor dangers of earthquakes. So the vertical precision of measurement is very crucial. So even 40 years ago, almost 40 years ago, in 1983, the vertical precision using advanced receivers was very, very, very good antenna, with very good data processing. It was possible to obtain precision 12 millimeters. Then, in 10 years, almost 2.5 millimeters. Then suddenly 5. And the current research is reporting precision of almost 1 millimeter. What happens between 92 and 95? Let's look the last column, and we'll see the number of solution days. This means that to obtain such a precision for geodetic application, for other applications, for example, quite popular now, autonomous vehicles, for precision agriculture, with robots, for other purposes, we need not to measure once, as we do in our navigation devices. We need to accumulate information for a number of consecutive days from a receiver which is stationary established, say for 3 days, or 19 days, or 5 days, or in that period in 1999, it was for 11 days, accumulating such information, processing it. It's possible to obtain precision of 1 millimeter. So claimed precision in 3 centimeters is even not enough. Good. So we understand that the targeted precision, millimeter, 1 millimeter or better, is quite high. How can it be achieved? The data, the input data, as I told you, are tabulated X, Y, and Z coordinates of the satellite with a time step 15 minutes. How can we obtain positions between such quite large step? Then try to use the usual polynomial Lagrange interpolation. It's a standard recommended, officially recommended technology. So you can see formula once, which is standard formula for Lagrange interpolation. TIs are the points with this 15 minutes time step when we know positions of the satellites. T hat is nothing but the target point when we want to find this position of the satellites. And with this simple formula, you obtain the result. Similar formulas can be given for trigonometric and other interpolation methods. What is new in our approach? And we call it free interpolation. Namely, let's look at the functions alpha i's of t hat. They depend certainly also on ti, but the main dependency is on the target position t hat. And suppose that we do not fix them here to be polynomial. It's polynomial in t hat in Lagrange approach, but or trigonometric in other approaches. But let's take a free form function, no limitation on the explicit or implicit form of this function. So they are absolutely free. That's we call it free interpolation. Obviously, it seems to be strange. How can one find, instead of one function f, which is, suppose it's known, we have a number n functions which are unknown, and we cannot, from this simple equation, fix such functions? No, it's possible. Make a simple trick which will result in a great accuracy increase. Namely, with these simple tricks, we take 100 more accurate results. And the trick is very simple. Let's fix t hat. What do I mean by fix t hat? How we do it? First, formally introduce a new definition, which I call very simple, interpolation pattern. Let's fix on the time axis the moments ti where the function is given, the nodes of interpolation, and nodes of them with 15 minutes time step, and the position of the target point t hat with respect to these points, when we have sp3 data. The picture is as follows. It's a part of, well, formal trajectory of our satellites, and white circles are known positions of the satellites on the trajectory. I took 6 of them. And by the way, 15 minutes time step between consecutive points corresponds to approximately 3,500 kilometers between them. And the target point in black circle is somewhere in the middle, suppose, here. But it's not the interpolation pattern. It's just a geometrical picture of trajectory. And the interpolation pattern is formally just very simple. On the time axis, I fix only such round white circles or crossed circles, the interpolation nodes, and the black circle, the target points. Here we see that we have actually extrapolation. 6 points from 0 to 5, and one more point when we want to obtain the coordinates of our satellite. So we called such 7 points in this particular case, or maybe n plus 1 point, the interpolation pattern. And the main thing is just to fix mutual position of interpolation nodes and target point. Good. When we fix t bar in our formula, in our general free interpolation formula, then dependence on t hat is not essential. Then our functions become constants, which is much better. Good. What is done next? We come to the following formula. When we fix the interpolation pattern, endpoints interpolation node, and the target point, target time moment t hat, we have the following same formula with unknown constant alpha i's. Now shift this pattern, the interpolation pattern, along the time axis. So for some moment, for the known sp3 trajectory, we take first 6 points, then shift 15 minutes and take another 6 points, etc., etc., etc. So we obtain a system of equations. What is known as such a system? What is not known? First, we know f in nodes ti. We want to know f in t hat, and also we want to fix alphas. So what is done? At this stage, at the first stage of training our interpolation formula, we need to know in advance some set of model trajectories where we know the left-hand side positions. So we now look at this number of equations as a system of equations for the unknown alpha i's, where right-hand side f and left-hand side f are known. Then we solve them with least squares methods. So we certainly have some residues, some small epsilons, such that the number of equation k is more than n, then certainly system is overdetermined. We have a lot of positions of our satellites, a lot of solutions are known. So solving such an overdetermined system, we obtain alphas such that sum of squares of epsilons is as small as possible. So now the time comes for the second step, using such alphas. So the first step, the training step, we did it, and it involves a pre-computed trajectories. In order to obtain alphas, we need to know the left-hand sides. Suppose we have computed 100 or 1000 trajectories, which is easily done using differential equations. We need to do this on the training stage. But as soon as we found such simple 6 alphas, for example, 6 or 10, not more, we go to the user stage, and we don't need to know pre-computed trajectories. We only know to have 6 constant alphas and sp3 points obtained from open data of trajectories. Good. But good, we fixed the head, but we need to know different positions for different time moments. So what is dependent on this t-hat? So we can go to the next step. We call it defrost t-hat. What do we mean by defrosting t-hat? For each particular position of t-hat with respect to our interpolation node, we compute alphas. Then we shift t-hat and again freeze it, we fix it, and again do the same procedure of training our model using our known trajectories and known position of satellites and obtain another set of alphas. And here on the graph you see the variation, the process of moving our t-hat target point from the first to the 6th point. Anyway in between, alphas change, and by the way, precision is around 12 decimal digits in our experiments. So alphas are known with high precision, and they look quite similar to something we understand as smooth solutions. And in fact, they are solution of the perturbation equation, but let's skip it and go to comparison. Go to basic steps of our algorithm again, summing up our approach. So free interpolation algorithm, as we do it, and we'll develop it further for the nonlinear interpolation, for multi-parametric interpolation, consists in 2 steps, which is very typical for machine learning approach. First, choose interpolation pattern and the model of free interpolation. Model means that we will do it nonlinear with some additional terms. We do it multi-parametric on the next slides. Then calculate training set of satellite trajectories using solving differential equations, certainly fitting such trajectories to available sp3 points. And we are grateful to our colleague from Siberian Federal University, Yuri Ushakov, who did this. And it's a very serious work, but it's done. It's commonly known. Well, after this, we train our set of our model and find the unknown coefficients alpha. And we should find this set of coefficients for quite a few positions of our target time points. In our experiment, we took 1 minute steps with t hat. So instead of 15 minutes in standard input data, we obtain positions with step 1 minute on this training stage and have coefficients for such training position. Then on the user stage, take this grid, calculate satellite coordinates at several points in such grid of t hat k, and use secondary usual Lagrange interpolation from the found points. What is the gain of this procedure if you still use some Lagrange interpolation? Because first, we need much less points from the input SP3 data. Second, the order Lagrange interpolation will be also quite low. It's enough to take 4 consecutive points with time step 1 minute instead of 10 points or even more for Lagrange interpolation with the time step 15 minutes. Let's compare accuracy of our approach and the standard Lagrange approach. Certainly, we have some differences for our satellite systems, for GPS and GLONASS. They are quite similar, but a bit different, because trajectories are a bit different, right? In the second column, you see the number of points in our interpolation patterns. And we see that for 6 points for 10 points, if you take 10 consecutive points with 15 minutes time step, then already Lagrange interpolation gives precision better than 1 millimeter. Good. But what if you take not 10, but say 8 points? Then precision obviously degrades. And for 6 points, precision is dramatically insufficient, more than 1 meter, if we use Lagrange interpolation. But with our free interpolation approach, the same number of 6 points is enough to reduce the error, root mean square error, RMSE, to 3.5 millimeters for GPS and 1 millimeter as a bit more for GLONASS satellites. So we see that with a simple approach, we gained more than 100 times better result than for standard Lagrange interpolation in the case of 6 points. Why 6 is important? Well, it's physically obvious. Satellites' trajectories certainly are influenced by external forces, but also they are obviously 6 parametric in a sense, because the initial position, three coordinates plus initial velocity on each cycle is essential. So it's, in a sense, number of parameters in trajectories is 6. So less than 6 parameters is not possible to take as input data to obtain a precise result. Good. Is it possible to move a bit further from such number 6 in necessary positions of 15 minutes grid given by processing centers of satellite navigation systems? Yes, it's possible, because in fact, in our simple approach and the classical polynomial and trigonometric and other approach, we process and we interpolate each coordinate x, y, and z separately. Why don't we mix them? In the standard interpolation approach, it's a strange idea, but in our free interpolation approach, there is no problem. So the first move, the first idea realized is just try to use in our interpolation formula all 3 coordinates when you want to find any one of coordinates in your target point t hat. Good. Well, precision a bit, well, error a bit smaller becomes, but not dramatically. But let's come with another idea. Why we take only linear combination of our input data, input points of satellites trajectories with 15 minutes time step? Why don't we take, say, quadratic terms? So let's unite x of ti's, z of t, or sorry, it's y of ti should be. So x, y, and z in the known points in one set of coordinates and take quadratic terms. So all possible products of x's, y's, and z's in all possible positions ti, right? With some unknown coefficients. That's possible, no problem, formally. Is it possible to gain something in such an approach? Yes. This nonlinear interpolation approach with free coefficients after training step and after testing of other trajectories turns out to be quite successful. We can now reduce number of points n to much smaller values. Certainly, if we take 2 points with all three coordinates, so still 6 parameters. So it's minimal number, obviously. If we have 6 parameters, so 2 points with x, y, and z coordinates, 1 point and another point, then it's possible to do nonlinear interpolation. And for degree 1, for linear case, certainly we have only very, very bad precision, 200 and something meters for extrapolation forward, and interpolation with t-bar in the middle. For degree 3 terms and degree 4 terms, precision is much better, but still not very far from being 1 millimeter. Well, why? Let's think about that. But another possibility is just to take instead of 3 points as input data in our formula. So take 3 consecutive nodes of our interpolation pattern, and instead of linear
Sorry,
interpolation,
Сергей, осталось меньше 2 минут.
Okay, we should make an interruption for reloading Zoom. Okay, I will just stop here.
Можешь поговорить.
Okay, for this table, it's okay. So we see that for 3 points, for linear interpolation, precision is not good. It's almost 45 meters for extrapolation, 1 meter, a bit more for interpolation. For degree 3, situation is very good, 3 millimeters. And almost 5 centimeters for extrapolation for the next 15 minutes forward position. And for 4 points, we have perfect millimeter, less than 1/10 of millimeter precision for degree 3, and even perfect 4 millimeter precision for extrapolation forward, 15 minutes forward. Okay, let's switch to our Zoom. Okay, let's zoom.
Okay. Sergey.
How can we get that?